Last time we introduced the supply and use framework that I told you is the generalization of input-output. Why? Because we introduce explicitly the difference between technologies and products. So we put a bit of nomenclature, what are products, environmental transactions, technologies, and especially how these are arranged in a series of matrices. Do you have any problem in interpreting the content of such matrices? The use matrix, the make matrix, environmental transaction matrix, all clear? Perfect. So what's the most important point to be understood here is that basically we are defining technical coefficients, here use coefficients, U, again as a function of technology activity. It's not working, okay? Okay, that works. And then we take the fundamental accounting identity that provides the sum of intermediate and final demand as the total demand Q, big Q, within the supply and use framework. And then we substitute the use table based on the equation that defines the use coefficient. So we express the intermediate transactions as a function of the technology activity. And then we approach finally to this equation here. I just started. So, and then we approach this equation here, where the total demand of products, Q, so this is in terms of shape, this product by 1, equals the intermediate demand of products defined as a function of technical coefficients or use coefficient in this case, and technology activity X plus final demand, Y. So again, final demand is product by 1 because the final demand is defined in terms of products. Does it make sense, right? You are invoking for products. So final demand Y with Y is product by 1, or by multiple demand agents defined at multiple columns, depending on the model. While the use table is product by technology, and the X is technology by 1. This is the activity. So T and T cancel out, and then you have an equation that is defined homogeneously as product by 1. That makes sense. Okay, then, while in using input-output analysis, we just look for the total technology output, so the total X. You remember that we wrote an equation like X is a function of what? Of I minus small z inverse times Y. So here was easy because we have just one unknown, one endogenous parameter of the model, that is X. While we have all endogenous parameters usually, we have the technical coefficient matrix Z, and then we have final demand, and these are usually known values. So we know these are exogenous parameters in the model. Here we have a problem because we have the U, that is the use coefficient. These are usually known values. This is something that we can gather from the literature, from gray literature, scientific literature, or from industry directly. Then we have the final demand, that is the reason why the system exists. But then we have two unknowns, Q and X, so the demand by products and the activity by technology. And that's why we stress the need of finding another equation in order to get the link between the Q and X. So we need to find a linear transformation between the Q, the total demand of products, and the X, the total activity by technology. Then I told you that since we don't know anything about this, we don't know nothing about this system, how it works. We don't know how these technologies are really working, operating from the physical standpoint. We have just some accounting tables, we have just some coefficients. We know the amount of input per unit of activity of each technology. We don't know what is lying behind the numbers. We don't know any rules, any law of nature behind these black boxes. But we know that from the mathematical standpoint, we can elaborate the data that we have in two opposite ways, by making two very opposite assumptions with two radical economic meanings. So we have on one hand the so-called industry-based technology assumption, and this means that, long story short, each technology, each product is produced with a defined and fixed mix of technologies. If I'm asking for heat, for an extra unit of heat, then this heat will be produced by all the technologies that are producing heat either by primary or secondary product with fixed shares. On the other hand, we have the product-based technology assumption. So with this other technology assumption, we are assuming that, on the other hand, each technology activity, when the technology is turning on and is producing, then such technology is producing always the very same mix of products. So if a technology like a steel factory was producing an amount of steel, an amount of heat, and we have such data, we got the product mix matrix, and then we are assuming that anytime such technology is producing, then it is producing the same byproducts, multiple outputs with fixed shares. Any doubt on these two opposite views? Now, here's the thing. None of these are right. Okay? So we are engineers. We know that engineering systems are very complex. They can work with very complex rules bound by very well-defined laws of nature. So it is not said that systems are working like this. But these are two opposite views that offer us two different ways of modeling the system from the point of view of the economic meaning and significance. Okay? So this is the idea. So we don't know anything about how the system works. We can rely on these two assumptions. But basically, these two assumptions means that we need to get the data about how the products are produced by technology. So we are now looking at this part of the supply and use table, the part of the make matrix. And then we are elaborating such make matrix in a way that we can get two matrices, two coefficients matrices, that will serve us to get the second equation, the relation between Q and X. So on one hand, we are getting the market share matrix, D, small d, that is simply the product between the make table, make matrix, and the inverse of the diagonal of Q. So we are dividing all the items in the columns by the total demand of product. So for instance, in this case, you see that we have 19 and 10. We are dividing each number by 100. That is the sum of 90 and 10. So we know that anytime we are asking for an extra unit of product 1, that is a good, in this case is a good amount of goods, then 90% of these products are produced by the goods sector and the rest is produced by the service sector. Then on the other hand, we are determining the product mix matrix. That is, you see, just another way of elaborating the make matrix. Instead of dividing P by the overall total demand of products Q, we are dividing the transpose of V by the total activity of technology. So we are just getting this matrix here, where the column, that all the columns are, again, summing up to 1. And here, this column here, you see that with respect to D, the dimensions are transposed. So here, while the D was a table of shape technology by product, here the C is product by technology. So what does it mean, the second column of table C? Any suggestion from your side? We have 0.09, 0.91. What does it mean?
Distribution percentage. From the table B and X.
Yeah. So we are transposing B, so we have 10 and 19, by dividing by the total activity. So we are dividing, you see, 0.09 and 0.91. It results just from the calculation of 90 divided by the output, 10 and 100 divided by 110. So we have that anytime the activity of the service sector is increasing, the service sector is producing 9% of goods and 91% of services. Okay? Are you getting my point, guys? You see that these are the two radically opposite way of looking at of defining how a system is behaving. Clear enough? Okay. So remember, we defined the d, and the small c, and then we made one practical example. So let's consider here a system that is composed by a heat plant and a steel plant. We provide we fill the supply and use table, and in this case is just defined by the make table, because there is just the demand y, and there is a make table. There are no intermediate uses. There are no environmental transactions. Then once we get B, we calculate, of course, the total demand of product and the total activity by technology, and both these can be derived as the row or column sum, respectively, of V. And then by dividing the V by Q or X, we can get the market share and the product mix. And I hope you had time to rehearse about the meaning of the unit of measure of these two tables. Do you want me to come back on these concepts? Should be clear enough. Great. So you see here we have 0.75, 0.25, and the sum is 1. And here in the second column we have 0.67, 0.33. So these are just shares. Pay attention that in case, and we are coming back later on this point, in case the activity of one technology is composed by multiple products quantified in different units, the sum of such values has no practical sense. From the mathematical standpoint, it works. Equations are always there, always valid. They are leading to a meaningful result. Not always, we will see some exceptions. But from the physical standpoint, we are just not defining any unit of measure for this total quantity. Because, for example, in this case, for the steel plant, we are just summing 10 tons of steel plus 20 megawatt hour of heat. The sum is 30, fair enough, but the meaning of this 30 is simply not defined. These are just unit of activity. Keep this in mind, we are coming back to this point later on. Once we are defining D and C, then we can apply now we made some examples here, maybe it's nice to revise these examples also. We have this double-entry table, so we have the first column that refers to the industry-based technology assumption, and in the previous system, remember we have this matrix D here. Then what happens with industry-based technology assumption if we are asking for 100 megawatt hours more of heat? What is happening? Let's come back to the scheme here. And the two tables. What is happening if you are asking, once we are defining and characterizing the model based on such coefficients, what is happening according to the industry-based technology assumption if we are asking for 100 megawatt hour more of heat? How is the model replying to this shock? Remember that this is what's the meaning here? We have a fixed share of output for each product. So we know that if you are asking for, by looking at the market shares, if we are producing 1 unit more of heat, then this will be distributed according to the shares provided by the columns of the market share matrix. So we have fixed market shares. So I expect that according to the industry-based technology assumption, 75 megawatt hour will be produced by the heat plant and the rest from the steel plant. Let's see here. Yeah. So we have 75 produced by the heat plant, 25 megawatt hour produced by the steel plant, and 0 tons of steel produced. Does it make sense from the engineering standpoint? Assuming that the steel plant is producing heat as a byproduct and not a subsidiary product, does not really make sense. Do you agree with me, guys? Okay. So here's the point. There is not a correct assumption, okay? All these assumptions are wrong. But the point is that I'm supposed, as the analyst, to select the best assumption that fit better the case that I'm studying. So in this case, I would reject this assumption. Why? Because there is no way of operating the steel plant without producing steel, but providing its byproduct, the heat. This is a kind of dumb way of operating a steel factory. Do you agree with me? The implications, look, the implications of these assumptions are really huge. And when you see, and when at the beginning of the course, I was speaking about the bottle. We have a bottle of water with some labelings. We have 10 kilos of CO2 per bottle, okay? But what are the assumptions behind this? I was exactly pointing at this. What are you assuming along your supply chain? Are you dealing with this technology according to an industry-based technology assumption or product-based assumption? Because the implications of these are really, really relevant from the point of view of the mathematical results. Indeed, if you are asking for, you see, let's take now the other way around. So what happens if I'm still invoking for 100 megawatt hour of heat, but then reversing and changing the assumption? So instead of considering industry-based, I'm considering, I consider product-based technology assumption. You see that here, this assumption is telling you that whenever I need one extra product, then the technology that is producing such product as the primary product is producing it, is satisfying such demand, but is also producing all the byproducts according to a fixed product mix. So in this case, we have the heat plant that is just producing heat. So no surprise, we are asking for 100 megawatt hour of heat, and just the heat plant is producing. This maybe is making more sense. But again, you as the analyst, you have to be aware about the meaningfulness of our assumptions. Then the other way around, we have the final demand, 100 of tons, by the calculated according to the industry-based technology assumption. So in this case, you see that the steel plant is producing 100 of tons because there are no other options for producing steel. But we are not producing the side product of the steel factory. This also may be not really meaningful from the engineering point of view. But maybe in other case, like I mentioned last time, the Yamaha, the company, that maybe in case of subsidiary product, this assumption makes sense because I can reduce and even put to zero the production of pianos, but I can produce extra motorbikes. So depending on the technology that I'm analyzing, then one assumption may be better than the other. And then the very last case, I have here, and this is the trickiest, because in case I'm invoking for 100 tons more, according to the product-based technology assumption, what is going to happen to the system? Since this steel is primarily produced by the steel plant is increasing its activity and is satisfying the demand of such amount of steel, 100 tons. But then what is also happening in the steel plant? According to this assumption, each technology is going to produce not just the primary product, but all the primary and secondary products according to a fixed, defined percentage. Product mix. This is fixed. So what is going to happen? If I'm producing 100 tons, based on the product mix matrix, I'm producing also 200 megawatt hours of heat. Now, from the point of view of the mathematical model, the model must satisfy a balance for the demand of products to work. So the point is that since nobody is asking for this 200 megawatt hour, there is no intermediate demand, no final demand, we have, from the mathematical point of view, compensate the extra production of this product by reducing its production by means of the only technology that can do so. So the technology that is producing this side product of the steel plant as the primary product, that is the heat plant. Are you getting my point, guys? Great. So I'm now introducing one point that will come back later on. I can apply product-based technology assumption only in case my system there is at least one technology that is producing the byproduct of another. I cannot just provide a system that is composed by technology with joint products. Because if it is the same, if this is the case, there is no technology that is able to compensate the extra production of the byproduct. And so the system won't be, it's not possible to solve the system of equations. We will see this mathematically now. Let's start first from the industry-based technology assumption, and let's now conclude and end the derivation of the Leontief models. So, let's start from the market share matrix. So we have the small d, we calculated this in the previous slides. So it is just the multiplication of v times the inverse of the diagonal of q. Now, if we are post-multiplying each side of this equation times the diagonal of q, we are getting identity in the second right-hand side. And so we can get this equation here. V times diagonal of q equal to v. I assume that these very simple modifications of the linear algebra expressions are so clear to everybody. Then from here, if I'm post-multiplying each side of the equation by the summation vector IP1, so I'm calculating the column sum of these expressions, I'm getting, here you see, as the right-hand side, the market shares, the make matrix times I. So it's the column sum of V. But this is simply the X, is the activity, the total activity. Remember that if we have V, this is the V table, if we are summing all the columns this way, we are getting the X, total activity. While if you are summing all the rows, we are getting the transpose of Q. You remember the structure of supply and use tables, right? Okay. So since we got this expression here, we can now substitute here the X on this left-hand side. We remember that simply the diagonal of Q times IP1 is simply equal to Q, and we are approaching the very final linear transformation between X and Q. So we got X equal to D times Q. Finally, we got our final expression here. Remember that we were looking for a linear transformation between Q and X, and we are finally approaching to this. You see, by simply defining one neat elaboration of make coefficients. So X equal D times Q, and it is consistent from the point of view of the dimension, yes, because we have technology by 1, is the X, equal to technology by product, that is the market share matrix, times product by 1, that is leading to technology by 1. So this is consistent. And this is our first equation that can lead to the definition of the Leontief production model, or primal model. Now, before moving on and deriving the Leontief model, let's also derive with the very same approach the product-based technology assumption and the linear transformation between X and Q of product-based technology assumption. We simply need to take the basic definition of the product mix matrix, then we are elaborating a bit by very simple manipulation of such tables, of such expressions. We get an expression that ultimately, at the left and right-hand side, lead to the column sum of the transpose of V. So this is simply the row sum of V. And this is the end is Q. So we are substituting the Q in this equation here, and we are getting the second linear transformation between Q and X. You see that Q equals C times X. Now, if I have to express the equation in the same way of the previous one, so X equal to, I'm simply inverting C. So I'm pre-multiplying each side of this equation by inverse of C. u equals to minus c x, okay, x, and the inverse of a matrix times the matrix equals the identity. So x equal to the inverse of c times q. Now, here's the thing. Previously I mentioned that it is possible to apply product-based technology only if the number of technologies equal the number of products. So there is at least one technology in my system that is able to provide as primary product the byproducts of the other technologies. This way, I can invert the product mix matrix C. Otherwise, there's no way I can get the inverse of C. This is the mathematical reason why I cannot apply the product-based technology assumption to a non-square system, a system that is composed by more products than technologies. This is the mathematical reason, and the practical reason is that if I had the previous example without the boiler, without the heat production system, according to product-based technology assumption, I cannot close the product-demand balance because there won't be any technology that is able to compensate the production of my byproduct, the heat from the steel sector. Clear, guys? Easy. Do I have to rush a bit more, or it's fine with this? Rush more? Yeah. No, it's okay. Okay, great. So remember that now we have the two equations here. X equal to something, sorry, x equal to something times q. Now, here's just two examples. Focus on this first and this second example here, where I just calculate the two, I just put, let's say, very clear what are the numbers behind each matrix or vector. So we have d times q equal x, and you see that in this first case, I have the market share matrix times q, and this is leading to x. You can do it even pen on paper. It's so easy. I recommend you actually to try to perform such simple calculations at home in order to understand the meaning behind the numbers. While you see that in the other case, when I'm relying on the product-based technology assumption, something curious is happening. If you see, this is the product mix matrix. So this is exactly the matrix that we have looked at in the previous slides. What is happening if I'm inverting this table? I'm getting a matrix with transposed dimension. So you see that while C is a product by technology table, the inverse of C is technology by product table, and the meaning of the number is what matters here. Because you see that we have the technology activity per each product demand. Here in this case we have 3 activity by the steel plant for each technology that for each tons of steel product that is demanded. And here we have the side effect of this production. So we are increasing, in case you are looking for 1 extra ton of steel, this is saying that the steel plant is producing 3 units of activity, so not just the ton of steel, but also the 2 megawatt hour of heat. But what is happening also, there is a -2 here. So whenever a ton of steel is invoked for, then also there is a reduction in the production of heat by the technology that is producing heat as a primary product, so the heat plant. So you got the meaning of the numbers. Try to figure out by your own also how these matrices are working. But here the important thing is that there are negatives here. And now the point is that researchers are questioning a lot of time about the meaningfulness of such negatives in tables. Because actually from the physical standpoint, if I have some negatives, it means that something is disappearing from the system. Now the point is that this should be seen as a kind of avoided emissions or savings in emissions. But again, it depends on it depends if this assumption is reasonable with respect to the system that I'm analyzing. If it is reasonable for you that when the steel plant is working, then also heat is going to be produced, and this is also expected to be recovered, and it will present actually a saving in natural gas consumed by boilers, then it's right. The product-based assumption is the right assumption for you. Otherwise, just get rid of it. And then, of course, there are no limits to because this is just a starting point. Then, based on your skills and your, let's say, also your creativity, you can provide more sophisticated formulation of Leontief models in order to, for example, account for the curtailments. Maybe you can relax this negative outcome, negative numbers as outcome of the product-based technology assumption by adding to the equations other pieces of the puzzle, by adding some possibility of the system of wasting and curtailing outputs. These are more advanced application of the impact assessment model that are trying to go more closer to the real way the systems are working, are operating. This is something you will deal with during the hands-on. Questions, guys? No questions at all. Okay. So now this is the primal model. Now, once we have, oops. Now, well, let's start now by arriving at the endpoint. That is the Leontief production and price models and the calculation of the impact. Now we have, with the industry-based technology assumption, our two equations. We have the total product demand balance. So the meaning is that total product demand equals intermediate demand plus final demand. This must be always satisfied. Then we have the linear relation between linear transformation between the x and q. So we define the rule by which the system is going to be operated when an extra demand of products appears. So now by combining these two, finally, we are able to substitute such x inside here. So we are substituting x with dq, and we are getting an equation that is simply with one unknown, because we have q, so the total demand, equal u times d times q, that is the intermediate demand as a function of product demand, plus y, final demand. So if we are moving this piece of the equation here on left side, we have q minus u dq equal to y. Then we can group the q. So we have q times I minus u d equal to y. And then the last step. Of course, the I is an identity matrix with the appropriate dimensions. Remember that in this case we have U, that is product by technology, and then D, that is technology by product. So if I want to solve this system of equations, I have to define an identity matrix that is product by product. Okay, fine. So by simply pre-multiplying each side of this equation by I minus U times D, I'm getting finally the Leontief model. So I can get the primal model here, total demand equals to I minus U times D inverse times Y. And this is the total demand equation. So I can get the total demand once the technology is defined, U. Once I assumed the way technologies are increasing their activity in reaction to an increasing demand of products, so the D, the market shares, and then the Y, that is the final demand. Once I am getting these three fundamental elements, then I can get the Q, the total demand. And once I have the total demand, then it's simply a matter of multiplying, pre-multiplying by this total demand by D to get the total activity by technology. Why this is important? Because then, finally, I can get, I know everything about the system, because I know that once I know Q and I know X, I can derive directly the use table, the U. just by multiplying the U coefficients times X, or the V table, V times Q. Then you can imagine also the other quantities, extensive quantities like the impact, the big R, that we'll see in the next slide. Now, here's the point. This is very, 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 very close to what we have just seen in the previous standard input-output analysis, because if you remember, we had the total technology output X simply as a function of I minus Z, small z, inverse times Y. So what is representing U times D is actually the small z of the standard input-output analysis. The point is that the small z that we have seen in the first lecture is already embedding the assumption on how the technologies are producing their products. So 90% of the case when you are in companies doing impact assessments, calculating emissions, blah, 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 they are relying on standard input-output tables, so square matrices, industry by industry or product by product. Now the point is, each of these tables, the small z, are actually derived from supply and use models. So they are embedding one assumption. You are analysts, so you should be aware about the assumption that is at the ground of each input-output table, square input-output table that you're getting. Okay? Because I hope you got the point. Here, depending on this assumption, there are very, very radical way of behavior, in which the system can behave in reaction to an increase in demand of products. So now, pay attention. This U times D, look at the dimensions, is U is product by technology, and D is technology by product. So this final U times D is a product by product. So it means that this U times D can be seen as the product by product square technical coefficient matrix of the system. So this table is telling us, if you're looking at to all the columns of this U times D, of this small z, you are getting the list of ingredients in terms of products that are required in order to produce one unit of product. This is the physical meaning of such tables. So it's really like a cake that is produced by flour, by sugar, by energy, by whatever. Okay. Now, there are many other transformations we can make, but we will look at these at the end of this lecture in order to get, for example, the technology by technology table. So this is simply, we will see later on, D times U, that is technology by product times product by technology. If we are simplifying this expression, we will see at the end of this lecture, we have another transformation of the input-output table. Instead of providing the input-output table as a product by product table, we are providing the very same table as a technology by technology table. Now, the underlying assumption is the same, but the meaning of the numbers that you are getting there is very different. So, whenever you are looking at one database, and out there in companies, they are making extensive use of such kind of tables and databases, you have to be aware about the meaning of the numbers that you're looking at. So before start using a database, you should wonder, okay, which type of database it is? Which way you are collecting data? Are you relying on a product by product table or a technology by technology table? Which is the underlying assumption? Be analyst, not user. This is the idea. Then the other way around, we have the product-based technology assumption, and the procedure is always the same. We have the total product demand balance, that is the very same of the previous one. We have another way of transforming X and Q. So we have X equal to the inverse of C times Q. And now by substituting the X in the total product demand balance, we can get as well the Leontief primal model that you see is exactly the same as the previous one. The only exception is that instead of considering D, we are considering the inverse of C. So we are assuming another way, the system is producing and is reacting to an increased or decreased demand of products. So we have the balance here. So Q equal to U times the inverse of C times Q plus Y. We are moving the first term of the right-hand side, left-hand side. We are collecting these into this table here. That is the I product by product times U times inverse of C. That is once inverted will be the Leontief matrix product based times Q equal to Y. Then I'm moving to the next step and I'm getting the Leontief model, the Leontief production model. So you see that here the only difference with respect to the previous one is simply this piece here. We have the inverse of C here and the D here. So another way of elaborating the make table lead you to very profoundly different results. Okay, guys? The point is that at the exam, I will give you some text describing one production system or giving you some reference production system, some schemes of how the system is arranged, and you are supposed to be able to define the supply and use table, provide coefficients form, by understanding the meaning of these assumptions, provide the best allocation assumption for the, or at least justify the allocation assumption that you, sorry, not the allocation, the technology assumption that you want and that better fits your case, and then calculate and calculate the total product demand and total technology activity based on the Leontief models. This is what you're expected to do. Okay? Now, I'm just very rapidly move to the very final step. Here you see industry-based technology and product-based technology. These are the rows of this table. So I have the main two equations, okay? I have the total product demand balance, the total activity balance, and the same for the product-based technology assumption. Then what happens is that, what happens if I have to calculate if I have to perform impact assessment? So the first step is the most difficult because I have to define the technology assumptions, I have to provide and to define where the balance is, I have to calculate the total activity and the total demand. Let's assume that we succeed in doing so. The very final step is, okay, let's now calculate the environmental transactions. I'm modeling my system, by defining my technologies, etc. I'm calculating how the system behaves. And then let's move to the environmental side. So from the production-based accounting, there's just one equation that can be applied. Because in both cases, it is just a matter of doing the environmental transactions coefficients that are defined as number of environmental transactions by technology. And then if I want to get the total transactions, it's just a matter of cross multiplying the small r by the total activity. Because here is just a matter of calculating the total amount of transactions by technology. You with me, guys? So production-based accounting, simply one equation that is valid for both. On the consumption side of the story, things are changing a little bit because I'm changing the way I'm calculating the Leontief table. So the inverse of I minus the product of U times something. So on one hand, if I have to calculate the footprints of products, then I have to derive one quantity that is defined as one by product, because the footprints, as I said, is something that is a property of the product, not of the technology. Technologies are let's say, are the source of the environmental impact. You see, so the big R is expressing the transactions of environmental transaction between technologies and environment. So not surprising that the R has the shape of 1 by T. Emissions are directly caused by a technology, not by a product. For example, consumption of fuels is it's caused by a technology. Fuels is entering a technology, is transformed within a technology. But in case I have to provide the footprints are actually not really properties of technologies, but are properties of products. I always mention, let's calculate the footprint of this pen, remember, during the first lecture. So I have to provide the calculation and a consistent equation that express the footprint, so the emissions, the water, the land, the labor, whatsoever, per unit of output of products. So I have to calculate an RE. Remember, in our nomenclature, small RE stands for footprints. And this equation should be, this RE should be 1 by P. So how can I count for this? Let's check this equation here. I have the R, that is 1 by technology, times D. So it's like saying, I need the environmental transactions coefficients R, but these coefficients are expressed by technology. So how I can translate these coefficients expressed by technology to byproducts? I have one assumption, in this case, this first line, that is industry-based technology. So the footprints of my products, so better, not the footprint, but the small r, so the exogenous transactions per unit of technology activity, to be translated into unit of products, must be post-multiplied by D, that is my market share. In other way, I'm just allocating the way each technology is producing emissions, for example, when a product is invoked for. So I'm post-multiplying R by D, and remember that D is technology by product. So you see that now this RD has the shape of 1 by P. So the environmental transactions are now expressed by product. It's just some set of averages. Then I'm post-multiplying this by the Leontief inverse matrix. And in case of the industry-based technology assumption, the Leontief inverse is the one that we picked here. So I product by product minus U times the inverse. So in this case, this table is a product by product table. So I'm simplifying also the products here, and I got a final RE, so the footprints 1 by product. The important takeaway here is that I have one equation that must translate the small r that are transactions by technology to properties of products produced by the system, footprints. And so you have to pass through this equation by post-multiplying R by D and then multiplying by the Leontief model, by the Leontief matrix, Leontief inverse matrix. You remember, guys, this equation that was very familiar, very close when we deal with the regular standard input-output model. We are doing the very same stuff, simply expanding a bit and making clear the underlying assumption, okay? So there are not many equations in this course, okay? It is just few balances and then some Leontief primal and dual models. And then depending on the assumption that you're doing, these equations change slightly, but the fundamental structure is always the same. Then finally, once I have the RE, so the footprint, it's simply a matter of post-multiplying these footprints by the diagonal of the final demand. So I'm simply multiplicating the footprint, so the impact per unit of product times the total amount of products produced. Total products footprint RE. Now, let me clean up this equation a bit. What happens if I'm switching from industry-based technology to product-based technology? Basically, the structure of the equations is always the same. The only thing that is changing is this D here, that in the first case is changed with C, inverse of C, while in the second case also here is changed with inverse of C. So remember, structure of the equations is always the same. I'm simply relying on a different assumption. Is that clear? I hope so. Yeah. Now, there is a warning. We are speaking about this at the end of the lecture if we have time. The point is that in our example, the example that we did previously about the steel and the boiler, we had out of the steel 2 products quantified in 2 different units of measure. Steel was quantified in tons, and then the heat in megawatt hour. Now, what happened is that when you are relying on the industry-based technology, the synonym used in LCA discipline for industry-based technology is impact allocation. It means that in industry-based technology, what happens mathematically, we will see within a practical example, is that the impact of the technology is allocated over multiple products. If a steel factory is producing steel and heat and is causing a certain amount of emissions, such emissions are allocated on all its outputs according to an allocation key. Now, this allocation key in industry-based technology depends on the unit of measure. So if the multiple outputs of a system are quantified in, say, mass units, so kilos, tons, that's fine. We are allocating the emissions depending on the mass of the products. If these are quantified homogeneously in megawatt hours, then we are allocating such impact based on the energy key. We can use the exergy, for example. That is what you did in the thermoeconomics and energy modeling. We can use money. We can use whatever we want. But in case we have non-homogeneous units, then the allocation is not really meaningful because you are allocating the, I don't know, amount of kilos of CO2 over 2 different quantities like megawatt hours and tons. But what if I'm changing the unit of measure, like megawatt, I'm keeping megawatt hours and I'm quantifying and accounting the iron in grams? Numerically speaking, I'm allocating all the emissions to the iron because it has the highest number. So the 2 allocation keys are not really consistent. And so, this is just a warning, when I'm relying on industry-based technology, I want to calculate the, I can use the equations, the production balance, I can calculate the direct emission by technology, no problem with these equations, even if byproducts are quantified in different units. But when it comes to calculation of the footprints, this implies an allocation procedure. I have to allocate my impact over a multiple set of products. And this is performed according to the industry-based technology by allocating impact on products depending on particular keys, mass, energy, etc. So I must be sure that in accounting for the production of my byproducts, I have to account these in homogeneous units. When I have to use an allocation key and I have to elaborate the data in a way that the byproducts are quantified in the same unit. While on the other hand, in product-based technology, this is called in LCA discipline, it's called also system expansion. Because if you have a byproduct, then LCA, the impact assessment model, is expanding the system by considering a saving of the production of the same product. Exactly what happened with the steel and boiler. We had a byproduct of the steel factory, and the system has expanded in order to account for the saving of such byproduct performed by the boiler. So since there is no allocation here, we can either rely on the consumption-based accounting according to the production-based technology assumption, and we can use those equations there, calculating the footprint, specific and total footprints, without also having homogeneous units, quantifying my product with homogeneous units. We can perform an example now, so maybe it will become more clear. Are you a bit confused now, I guess? Yeah?
In the exam, in order to avoid this warning, I will choose always probability.
Yeah, but the point is that to me this is not really making sense because you are doing calculation right, maybe by selecting wrong assumption. If if I'm making the analysis of Yamaha products and I'm measuring my bikes, my motorbike in euros and my pianos in units, you have two different units of measure. Okay? If you want to apply the industry like this, the right assumption is the industry-based technology. The point is that you should elaborate your data in a way of having your outputs consistently measured in one units, instead of simply saying, okay, units are not consistent, so I'm changing the assumption. Because the assumption is telling you how the system is likely to behave. So it's something that depends on your, let's say, on the reality, on how the system works. Like the unit of measure is something that you, as the analyst, you can correct, depending on how you are defining the data into your model. Keep in mind this, and then we are doing an example, hopefully today, otherwise, yeah, today. Okay, so let's now have a look on the Excel file here. Maybe a bit better with respect to last time. Again, I uploaded this file in the WebP page, so you can see all these tasks here that are solved. I suggest you will need to practice at home in order to really grab the meaning, okay, of what we are talking about. So let's start from this example here that is very, very easy, and let's now perform together all the calculations inside here. We have the use of okay, first things first. Is the structure of this table clear for everybody? So we have the use table. You want me to zoom in a bit? We have a use table here that is 0. Is it clear why this table is 0? By looking at this reference production system? Yes or no? Yes, great. Then we have the final demand. That's fine. We have the make table here, and we have this is one addition with respect to the example. This is the kilotons of CO2 emissions in a reference time frame. So this is not appearing in the figure, but it's there. Now we have a total Q. So we have calculated the total demand that is equal to the final demand because we don't have intermediate one. Then we have the total activity. That is simply the column sum of the make table. And then we can check if the total product demand equals total the transpose of the sum of the transpose of V, column sum of the transpose of V, or the row sum of V. So let's just make it simple. Let's calculate the sum of the make table. We are getting here 80 and here 10. So it makes sense because this is nothing but the transpose of Q. Are you with me, guys? So I can say that the system is consistently defined. Tables make sense. Balances are respected. Great. Now let's calculate. So the use coefficient 0. That's 3 though. We have 0 in the use table. And then we have the environmental transaction by technology. So it's just a matter of dividing each of these numbers by the total activity by technology, the total X. Does it make sense to you? Yes or no, guys?
No.
No, why?
I lost
We are simply defining, let's calculate it cell by cell. We are calculating the small r are meant to be the environmental transactions coefficient per unit of technology output. So it's just a matter of dividing 70 over 60, right? And then we are dividing 30 by 30. And if we are adding some figures here, we get the very same numbers of these. Here I calculate these based on a linear algebra expression, okay? But there's no difference. Is the meaning of these numbers clear for you? Okay, great. Now let's calculate together the C and the D. Let's start from the D. So we have matrix multiplication of the make table times the inverse of the diagonal of Q. So the inverse of the diagonal of Q. We have Q times M unit 2. Close, close, close. Should work. Yeah. 0.75, 0.25, 0, 1. Let's now move to the calculation of C, matrix multiplication of transpose of V times the inverse of the diagonal of X this time. Unit 2. 0.67, 0.33. That's fine. Is the meaning of these two tables clear for everybody? Great. Let's now move down and let's apply, focus on this first block here. Let's apply the industry-based technology assumption. So recalculate the fundamental items here. So the total extensive quantities based on the industry technology assumption. That, by the way, in this case is the assumption that is supposed to be wrong for this case, right? Because we are engineers, we know that steel plant cannot provide tons of steel without producing heat. Or that cannot provide heat alone per se without producing steel. So, by the way, we are not technology experts, let's assume. So let's calculate also the result based on industry-based technology. So, what is the first block here that I have to fill? I do have to apply the LTF models. What is the output of the LTF models? Q and X. Great. So let's start from this Q here. That is the LTF primal model, total product demand balance. So Q equal to the matrix product multiplication of the inverse of the M unit, the matrix unit, so the identity matrix of dimension 2 minus the matrix multiplication of U, where is U, times D right. The inverse should write times array 2, that is y. Let's pick this y here so we can make some experiments. Close. And this, if I'm putting here 0, should work. Yeah. I have no final demand, so I have no total production. Right? What happens if I am now filling this matrix here with the very same number that I have here, 80, 60, let's here. Great. I have here my answer that is correct. Final demand equals to total demand of products. I have no intermediate demand. Indeed, if I'm multiplying, but first things first, let's now complete the LTF model by also calculate total X. That is the matrix product between the matrix D times Q. Should work. Yeah, 60, 30. This Q here is supposed to be capital. Does it make sense? Yeah, because I have here the same X. Does it work for you guys? Great. Now let's calculate first the R. So the emissions, the emissions are expressed by technology activity. So let's multiply the R, small r that we calculate here, up here, times the diagonal of X. So it's X times M unit 2, 70, 30. So I applied my LTF models. LTF model here according to the industry-based technology, and I got my the first most important result. So the total Q, the total X, and the total R. Then I know that I also can calculate the total U and the total V. That gives me a better understanding about how the system is behaving. We know that U is 0, so let's get rid of this calculation. But for the V, is it interesting to look at this? So let's calculate the matrix multiplication of D, market shares, times diagonal of Q. So picking here the Q, times matrix unit 2. Yeah, does it make sense? This is the base case. I have 80 and 10. And this is 60, 20, and 10. It makes sense to me. Sums are correct. That's great. Let's now do the same, the very same, with the product-based technology assumption. Now, for the sake of time, let's move to the already solved model, but it's the same. This is the very same model. I'm simply calculating the Q and the X in another way. So I minus, instead of UD, U inverse of C. And I'm getting the very same result. So first point that is interesting is that since I got my data starting from the same case, the very same table, the supply and use table above, then if I'm replicating the same condition in terms of final demand in these two examples, I'm getting the same result. You see that if I'm using industry-based or product-based technology, it doesn't matter if I'm relying on, if I'm asking for a final demand of 80 megawatts as heat and 10 tons as steel. Things are going to change if I'm changing the yield of my final demand. Because it's like saying that I have a model that is now linear, and that let's assume that I want to investigate the change in X by the heat plant and X by the steel plant. I'm starting from a point that is the demand of product of the two technologies, for example, in one defined time frame, and then I'm defining two different models that are like two different slopes. So if I'm getting the first final demand, I'm getting the very same solution by both. But the more I'm moving far from the initial conditions, the more the two behavior of the two systems diverge. And this is quite understandable. I'm relying on some assumptions that are, let's say, not the real way the system behaves. So I would have expected that the more I'm moving far from the original Y, the original final demand, the more the behavior of the system will produce different results. My assumptions are different. And this implies one very important thing, that when I'm doing impact analysis, especially when I'm looking at large-scale systems, I cannot rely too much on my output model. That is, I have to provide small shocks, or better, my results will be more accurate the more the shock is tiny. I can just deviate not too much from the equilibrium point, from the point that is represented by the snapshot of the table. If I'm deviated from this by applying very strong shocks, it is likely that we are moving far from where the system would have reacted and landed. So let's now play with this model. Pay attention. I got also the total and specific footprints of products, these pieces here of the tables. So you see first that in this first case, while I have the very same emission by technology, why? Because this is just a matter of accounting. I'm counting the emission that are exiting each technology. So I know that, quantitatively speaking, I have 70 kilotons of CO2 out of technology 1, that is the heat plant, and 30 out of the steel plant. This is something I can measure. So independently from the assumption that I'm using, I'm always hitting these two numbers. While on the other hand, you see here, I have the impact of such products. You see first that while the big R are below the technologies, so they are properties of the technologies, they are caused by technologies. In the case of impact and footprints, footprints are below the columns of the products. Why? Because these numbers here are no longer products of the technologies, but these are products of the products. Sorry, are properties of the products. And you see that here you have different numbers. So let's look first at the footprints of products. So you see that here we have the very same system with the very same final demand, 80 and 10, but we have here the emission embedded into the unit of product output that differs. They are different. Why? Because this strongly depends on the assumption, on industry-based or product-based. Okay? You see, this is a matter of allocation, because in the industry-based technology, you see that we have, where is this? The emission of this is the emission of P1, that is heat, you see? That is produced as a mix of the emissions of the boiler and the emission of the steel factory. And since the steel factory is emitting less emission than the boiler in the base case, then it turns out to be a number here in the industry-based technology that is smaller compared to the very same emission factor, the footprint of the heat in the product-based technology assumption. This actually is reflecting the way the system is behaving according to our assumption. That's why I was telling you that I'm getting crazy when I'm looking at numbers without specific justification and making clear the assumption, because it is so difficult to make models of physical systems, and there are a lot of uncertainties, and here there are orders of magnitude more uncertainty with respect to an engineering model. Because there is not just the uncertainty of the data, but there is also the uncertainty of the paradigm that we have in our mind about how the system behaves. In this one example, we have the very same data, but we have two different footprints. And the numerical result is heavy. The numerical difference is not negligible. Here, for example, you see that, here's another thing that is interesting. We have one emission, one ton of this is just one of CO2 embedded into a ton of steel. This is supposed to be kilotons of CO2 per ton of steel. These numbers are completely not real, of course, just for the example purpose. But here we have a 1, and why we have here 0.67, in your opinion? Why this number here is so small compared to the previous one? This, of course, depends on our assumptions. But why? Try to recall the example.
Steel plant probably has less, I'm not sure, less emission than heat plant.
Yes, of course, but not just for this, because in the end, it's not just a matter of comparing the two. Okay, here we have the same plants. So we have here the steel plant is the same. So we have steel plant here, steel plant there, and we have the very same emission factor. That is 1 kilotons per ton of steel. You see here up. So the emission factor, so the direct emission of the unit of activity is always the same. But in one case, we have 1 here. Because if you remember, if we are producing an extra unit of steel according to the industry-based technology assumption, what happened? Steel is produced just by the steel factory, and nothing else is happening. But this implies that we are somehow allocating all the emissions of the steel factory, produced by the steel factory, on the unit product that is going to be produced. That is the steel. Right? We have the heat, but it is not produced. So all the emissions are there. What happened here? 0.7, 0.67. If you remember, if we are invoking for 1 extra ton of steel according to the product-based technology assumption, what happens is that the steel factory is also producing heat, not just steel. And this heat is represented as a negative production from the boiler. So the portion of the heat that is produced by the steel factory turns out to be a negative production of the boiler. And this negative production means a saving in emissions. That's why we got this number here that is smaller, significantly smaller with respect to the previous case. And we could have also got a negative number if we are putting that would be the case of very high production of heat out of the steel plant. and very high emission factor from the boiler, it means that the savings that we can get from recovering the byproduct of the steel factory is significant. That could have led also to negative emissions in this case. But what is really important for me is that you understand that behind the models and these assumptions that there's an economic meaning. There's our idea about how the system is behaving. So this is not really deterministic. We don't have laws of nature that are telling us that, okay, I will drop this pen from here to there, it will take dot seconds. It's not behaving like this. We are in a post-normal science. So there are some assumptions. We have to be ready to be able to provide a scientific and solid justification about the assumption that we are doing. That's the most important thing I will ask you during the project work, okay, and during the exam. Okay?
Yeah. Can we say that if we have this deep plant situation which are higher value in industry-based technology, we say in the opposite way we have for sure that the other technology, in this case steel plant or heat plant in defense, has to be a lower value than the other. So 1.17 is bigger than 1.13, and necessarily it happens the opposite with the other technology.
I think it much depends on the technology structure of the system. This is a very simple. Okay, you can get this kind of general rules just because the sample is so small. It may seem to you that here we are overcomplicating something that is easy, and it's true for this case. But when you are analyzing very complex systems, it's not so easy to get some general rules, okay? But what you're getting is a behavior that is significantly affected by the assumption that you are making, okay? So you have to practice a lot and to test let's say, the corner cases of your model. So you have to stretch your model to see how the model is behaving with respect to a change in exogenous factors. Okay, let's jump back the very last. Okay, first, here there's the example. That is the example that we already seen with the same numbers, and this in the Excel. I put for you another example. That is example 2. Here, example 2, with the same structure, but in homogeneous monetary units, with also some intermediate uses. So you can practice also at home in writing equations and make calculations and understanding the meaning of the numbers. Okay, I warmly invite you to try to make this calculation by your own, and to come to the lecture with some questions about it. Maybe we can talk about this during the next hands-on. So you will practice with these numbers by your own. Now let's now move to a very interesting topic that is the let's say, from this slide we can start making models very wonderful and very complex, representing very complex reality and real world systems. When you are modeling input, output, or supply, you use models just with system of linear equalities. This is a kind of way of doing that is kind of imitating, because you have a set of linear equations, and you can get some results that are so, I would say, supine by the fact that we have just linear equations. So your model is not able to move a little bit more freely and find a solution that is in a broader space of feasible solutions. So the former case, the case where you are handling a system of linear equalities is the case of the standard, I'm calling it SCA analyst. You are relying on softwares. In the end, softwares are just applying the equations that we see in the previous slides for getting the results, the footprints, etc. That's fine. But if you are willing to use this kind of framework for modeling more complex systems, you have to relax a bit the, or better, you have to enhance the mathematical representation of the system. Instead of modeling and solving system of linear equalities, you can solve system of linear inequalities as linear programs. So you can define LP models. Let's look at this by defining an objective function and a set of constraints that are reflecting the way the system is behaving. But you can enrich this system with more constraints in order to find the possible solution space and increase the let's say the features of the model, of the mathematical model, and its ability to capture the physical reality. Now let's have a look to this LP system. You have an objective, for example, that in this model is the minimization of something. For example, the minimization of the use of factors. Usually, these kind of models, in case they are representing very complex systems like the energy system or the whole economic system, are minimizing the use of factors, so the cost of the system. Remember, in thermoeconomics and energy modeling, you define LP models of the energy supply chain. You minimize the cost of or the NPV or the annuities of cost, or either operating and investment cost of the system over the whole planning horizon. Am I right? I remember well about the curse of Emanuele Colombo. So here's the same. You are minimizing the total cost of factors. You see here there's R times X. Here R is 1 by T, so you have a technology, 1 or L number of factors. You can have labor cost, CO2 cost, primary energy cost, etc. times X, that is technology by 1. And then you have a pi, here a transpose of pi, that has the shape of 1 times L that represent the price of factors. In this kind of model, you may have factors that are quantified in physical units. We have seen so far tons of CO2, there may be square meters of land, there may be labor in terms of hours, and so on and so forth. You have to couple these with kind of factors like pi, that is expressing and collecting simply the prices of factors. How much does it cost them? An hour of labor, a ton of CO2 in terms of taxes, for example, and so on and so forth. So we are simply translating all the physical factors into value, economic value. So we can define this as a scalar, Z, and minimize this as the objective of my problem. Then I have to define a set of structural constraints, and these are, you can see this very clearly, is the product demand balance. So total demand of products minus intermediate demand minus final demand should be greater or equal to 0. Then we have one of these two technology assumptions. So we can select for the system to operate with according to an industry-based technology or product-based technology, or a mix of two. Because there may be cluster of technologies in my system that are better described by means of the industry technology, others that are better represented by product technology, depends. So we can also adopt some more sophisticated way of assuming how the system behaves. Then there are the non-negativity constraints, here, X and Q greater than 0. And then I can add a number of constraints, like, for example, what about the capacity of my technologies? I may have some constraints that are binding the way some technology are able to provide their products. Like, for example, in the energy system, I can provide some capacity constraints for solar PV. I can provide some constraints depending on the policies. For example, I want these the total emission of one particular sector to be gradually reduced, and so on. So once the system is defined, I have to inform the system with some exogenous variables here. So of course I'm defining the structure of the system, so I'm defining the use coefficients, the environmental transactions, the D or the C matrix, the prices of factors, and then once the system is solved, I can get my endogenous variables. So I'm getting the U, the V, the R, etc. So this is really, and I hope I have the time at the end of the course to let you see the energy system model of Italy that is defined according to this mathematical scheme. And I recommend you to practice a lot in defining linear programs with supply and use framework, because this could help you many times also for other disciplines. You can solve a range of problems. Anytime you have a productive system, you can provide a formalization in terms of supply and use. You can get a lot of benefits in terms of comprehensively providing a model that is really complete and makes you, enable you to understand how the system behaves and enrich the narrative about how the system behaves in reality. Okay, then I have a bunch of last things that I have to say, but very quickly, because from now on, just simply, okay, put this in a corner of your mind without putting much attention on what, sorry, put attention on what I'm saying, but do not care about these topics for the final examination, okay? Because these are a bit complex. You remember that for any primal formulation of the Leontief model, there is also a dual formulation. I stressed so far that for the quantity, Leontief quantity model, there is also a dual or price model. And we try to understand together what the meaning behind the so-called price index. Now, the point is that we can apply Leontief price model to input-output systems, square input-output models, simply, and that's fine. We got one price index. But actually, in reality, as like as you have the product demand and technology activity, you have also prices of products and price of average product outputs, so price of technology activity. So this duality is also reflected not just in the primal model, but also in the dual model, that is the one that I'm showing you here. So if you are elaborating the Leontief, sorry, the supply and use tables by introducing the prices of technology activity, Px, and the prices of technology of product output, PQ, you can define two equations. One that is the price balance for technology output, that is very close to the price equation that we have already seen, where you see that the prices of technology output, Px, equals the price of products consumed by each technology plus the price of factors. So it's exactly the same of the previous price balance that we introduced during the previous lecture. And then you can link the prices of products to the prices of activity by means of the usual matrices D and inverse of C. So again, also prices can be calculated and are affected in the same way of the primal model by the assumption that we are making industry-based or product-based technology assumption. Okay, forget about this. I'm not asking you this the final examination, but this may be important because in the end, in reality, we don't have just products. We have the average output of industries, and we can get some synthetic indicators about how the prices of one particular sector output is going to change depending on the shocks. So also useful information could be derived from this, from the application of these two models. Okay, some curiosities. What happens here if we have number of products different than the number of industries? Just have a look at this. And then here, simply to say that this may be important just to remember. Whenever you are applying the input-output modeling, especially during the final projects, you will find a lot of input-output tables out there. The point is that input-output table that you may find are 99% input-output tables, so product by product or technology by technology. You have to remember that always the root of such table is a supply and use system, where explicit mention, explicit distinction about product and technology is performed. Then these supply use framework is elaborated and translated into input-output tables, product by product or technology by technology, depending on the assumption that we are doing. So the square tables are actually embedding the information about the technology assumption, industry-based, product-based. So it's like saying that we are taking one table, and if you are taking one square table, we are also taking the underlying assumption without being able to change the assumption, to elaborate it. So we can find out there 4 types of tables: product by product or technology by technology, defined according to the industry-based technology assumption, or product by product and technology by technology, defined according to the product technology assumption. So anytime you find a table, you first, before start using it, you have to wonder about the type of table that, and which type of assumption is represented, and which type of table are we in our hands? Do we have a product by product or a technology by technology? It's very important because anytime we are doing analysis, we are applying some shocks, numerically speaking. So we are defining a demand, for example, a final demand. But in case we are using a product by product table, we have to remember that the final demand here we are defining must be defined in terms of product. Otherwise, if we are relying on technology by technology table, we have to remember that the final demand is the average output of a sector that may be very different from the product. So this is not an easy topic, I know. Indeed, I'm not asking you the equations for doing the transformations, etc. I put here just for curiosity. Expert analysts are never using square input-output tables, are always relying on supply and use models because these are more exploded, I would say, are more customizable. But 95% of the time out there, you will find people that are simply picking tables and inverting table and calculating stuff without really knowing what you're doing, okay? So be aware about this, because the numbers that you're getting from these tables may approach some, may be put in some reports that may also go in some desk of some policymakers. So if you're calculating something that is wrongly calculated with bad assumptions, it may have really, really serious effects. Okay. 3 p.m. So we are done, right? Fine. Stopping the